Welcome to part 2 of neurophysiology. In this part we're going to start to look at some of those neural pathways. So we'll start off looking at reflexes. Reflexes don't involve the cortex. And the simplest, of course, is the patellar reflex, so you'll know how that works, hopefully, by the end of this. So we'll look at some reflexes. We'll also look at the ascending sensory pathway and the descending motor pathway, back down to the neuromuscular junction that we talked about before. We'll talk a little bit about the autonomic nervous system, but that really comes into play in terms of what it does within systems. So we'll come back to it throughout this module and clinical reasoning. We'll then go on, we'll do a bit of revision about the action potential. Hopefully you can remember most of it. And then we'll look at how action potentials are actually generated. And this is through the summation of graded potentials. We have little excitatory or inhibitory graded potentials. They get summated to determine whether there's going to be an action potential propagated along an axon. Enjoy. So, as promised, let's start with some reflex arcs, and the one you know best, the patellar reflex. Now, the patellar reflex you'll see described as monosynaptic. There are other synapses, as we'll find out, but the key thing about this is, and this is what makes it a reflex rather than a pathway, is that there's no involvement of the brain. Nothing goes up to the cortex, and the cortex doesn't tell you what to do. So it's purely at the spinal level that this all happens. So starting from the beginning, of course, you tap the patellar tendon. Hopefully you hit the tendon. And this stimulates a muscle spindle. A muscle spindle is like a little specialist mechanoreceptor in the quadriceps. This mechanoreceptor, the muscle spindle, sends an action potential along a sensory neuron, which we now know is afferent, all the way up, as all sensory neurons, to the dorsal horn. The afferent coming in then synapses directly with a motor neuron, which then leaves the ventral horn. Remember, afferent comes into the dorsal horn, efferent goes out of the ventral horn. What that does is it sends the action potential back along a motor neuron to the quadriceps, to a neuromuscular junction, causes excitation contraction coupling in the quadriceps. They contract and the leg flips out, the leg jerks. And it's taken me some time to describe this, but as you know from your clinical experience or from your clinical assessment practice, this happens really, really quickly. It's a quick reflex. And it's so quick because, of course, it doesn't have to go all the way up to the brain and come all the way back down again. Hence, it's a reflex. So the patellar reflex involves, as we saw there, muscle contraction. We're talking about contracting the quadriceps to make the leg straighten. But in order to do that, we need to relax the antagonistic muscles. The physios amongst you will, of course, know this, that we can't have the muscles, so in this case, the hamstrings, contracting at the same time. We need to relax those to enable the leg to straighten, enable that contraction of the quadriceps to straighten the leg. So we have to have another little bit added on. So what happens is, if you look at the grey matter on the far right there, we've got our afferent is branching once it gets into the spinal cord. There are two synapses, One of these synapses is the one that we just talked about that causes the contraction of the quadriceps. The other one there is synapsing with an inhibitory interneuron, and the interneuron is acting like an off switch. It's preventing action potentials, inhibiting the action potentials from going to the hamstrings, so the hamstrings stay relaxed. So the sensory neuron also synapses with an inhibitory interneuron. The interneuron inhibits the motor neurons serving the antagonistic hamstring muscles. And here you can see what actually happens, of course, our action potential coming up our sensory neuron is going to split at that branch, go down both branches to both synapses. So therefore, it is exciting the interneuron. It has to excite the interneuron for the interneuron to do anything. But whereas it excites it, what happens is the neurotransmitter from that interneuron is an inhibitory neurotransmitter. It's not entirely accurate. We'll talk a little bit more about that later. But at one end of our interneuron, the afferent end, we're having the interneuron being excited because otherwise it'll just sit there fast asleep. But at the other end, what it does, it inhibits the motor neuron that's going to the hamstrings, making sure they stay nice and relaxed. This causes the hamstrings to relax, and of course, while the quadriceps are contracting, that will allow the knee to extend. This is another reflex. It's a reflex that we do quite often. It's the pain reflex, otherwise sometimes known as the withdrawal reflex. The concept being, of course, that if you touch something that hurts, I think the lady in there is stepping on some broken glass. She's doing that with her right leg. Of course, if you had to analyse and look down and go, oh, look, I've just stepped on some glass, by the time you do that, you probably would have stepped on it a lot heavier and done a lot more damage. So what you need is a reflex that will make you move away from it before you have time to think about it. And this is this withdrawal or pain reflex. Works in much the same as the way as the patellar reflex. But in this case, it's stimulated by pain, not by a patellar hammer hitting a tendon and activating a muscle spindle. In this case, we're activating nociceptors, pain receptors. But it results in the withdrawal from the source of pain. So a nociceptor is stimulated. This sends an action potential along the sensory afferent neuron, again, to the dorsal horn. This afferent neuron synapses directly with or via an interneuron, which may be excitatory or inhibitory, but ultimately it synapses with motor efferents, either directly or via interneurons. Again, no passage up to the brain, no passage down from the brain. Consequently, there is muscle contraction and relaxation. This is going back to what we were saying about you need to relax the antagonistic muscles to allow contraction of the other side, if you like. So we have a mix of contraction and relaxation involved in order to, in this case with this lady, lift her leg up, withdraw from the source of pain. If she'd put her finger on a hot plate on the cooker, she'd be moving her arm away. So there would be contraction and relaxation of the muscles in her arm. This is affected, as we said, through a mix of excitatory and inhibitory interneurons. sending action potentials out via motor efferents or inhibiting action potentials from going down those motor efferents. Again, as we said, this is a reflex. There is no cortical control. You are not telling your leg to lift up when it steps on some glass. By the time you realise, you will have done it. Of course, you know you've done it, and you know you've done it because of other pathways. And if you think about it, it's a bit like the patellar reflex. If you look away, even though it's a reflex, you know someone has hit you on the knee with a patellar hammer. But of course you know, because in order to hit your patellar tendon, you also have to hit some skin. That skin has sensory receptors, which will go up to the cortex, and they will tell you someone just hit you on the knee with a patellar hammer. However, you will have already done the jerk, because that's much quicker, because it doesn't have to go all the way up to your brain to be interpreted. And the same with the pain reflex or the withdrawal reflex. The withdrawal is going to happen before you realise that you have pain. Also, in the withdrawal reflex, another thing that might be important is the crossed extensor reflex. So in the left there, we've got the withdrawal that we just talked about. The lady on the left, same lady on the right. But here what we're illustrating is that she has lifted a leg up. Therefore, she needs to balance on the other leg. Now, to do that, it's going to take fine adjustments involving muscle contraction and relaxation for her to be able to balance. So we need to send this reflex through to the contralateral, the opposite side of the spinal cord, to go out to the opposite side of the body to enable balance. So in this case, an interneuron from the sensory neuron, the original one sensing the pain, may cross over to the contralateral, the opposite. Remember, contralateral is opposite, ipsilateral is the same. Contralateral side to the ventral horn. So this is the opposite ventral horn. This ventral horn has motor neurons serving the other leg, or in the case of touching a hot plate, the other arm. So in the contralateral ventral horn, it can synapse with other excitatory or inhibitory interneurons again, because again, we're going to need contraction and relaxation, which then synapse with motor neurons on the contralateral side. This causes muscle contraction or relaxation on the opposite side, which maintains posture and balance during withdrawal. And you might say, well, yes, that's all very well for legs, but what about arms? If you touch a hot plate, do you really need to move your other arm? Next time you touch a hot plate, just be aware of where your other arm ends up, because there's a high possibility that your other arm will move as well because of this crossed extensor reflex. So we have the reflex serving the affected limb to withdraw from the source of pain, and we have the crossed extensor reflex, which helps to maintain posture and balance during the withdrawal. Which brings us on to the sensory pain pathway. And I have highlighted in bright yellow there, this is not a reflex. This is what we were saying about, yes, you've done your withdrawal, but of course you're aware that you've stepped on glass because you have pain. So it's not a reflex because it's going to go all the way up to the cortex. It is stimulated by that same sensory neuron that was engaged with the withdrawal reflex and the cross-extensor reflex, but it has another branch. So they all branch out. So you have all these possibilities of synapsing with different neurons. This branch is going to carry the sensation of pain up to the somatosensory cortex. So, as we said, our nociceptors on the free nerve endings are stimulated. These are the same nociceptors that are causing our withdrawal and our cross-extensor reflex. An action potential is then propagated along the primary afferent neuron. It has to shoot up into the little soma of the neuron, because remember, sensory neurons, they have their soma halfway along the axon, so it has to go up into there in the dorsal root ganglion. We'll talk more about that later. It then carries on into the dorsal horn. Here it synapses alongside all those reflexes with the second order afferent neuron. So the first one is the primary afferent, the second one is the second or secondary or second order afferent. This second order afferent crosses over to the ventral horn on the contralateral side. Remember, it's going to leave the ventral horn. It then needs to get up to the brain. And it gets up to the brain, it ascends the spinal cord via tracts. Tracts are like nerves within the central nervous system. This pathway is called the spinothalamic pathway. It involves the spinothalamic tract and the spino-reticular tract. At the thalamus, the second order afferent then synapses with the tertiary or third order afferent neuron. And you remember we were talking about the thalamus before as the precortical relay point. This is, if you like, the relay point. This is where we have our second synapse in the pathway. This tertiary or third order neuron then travels up through little tracts in the brain to the relevant area of the sensory cortex. So if it's a hand, it will go to the hand area. If it's foot, it will go to the foot area of the somatosensory cortex. The sensory cortex then perceives the nature of the pain, and that sometimes will depend upon the type of fibre. We'll get onto that quite a bit later. But it can also perceive the location of the source of pain. You know, oh, my foot hurts. Oh, look, I've already lifted my leg away from it, but it still hurts. So it's a slower pathway because it's got to go all the way up to the brain, but it's stimulated by the same stimulus that stimulates the withdrawal and the cross-extensor reflex. They're reflexes then because they don't involve cortical control. They remain at the spinal level, if you like. This is a pain pathway because it goes all the way up to the brain. As a result, you've already moved your leg, so what you might do is shout or scream. Okay, so that's a sensory pathway, and that's our reflexes. There's a few other reflexes around that help protect you from muscle stretching, from overexertion, and that's what, if you try and lift too heavy a weight, might make you drop it. It's a reflex due to sensors within your muscles, and there's various reflexes like that. Okay, so again, we're now going to have a pathway, but in this case, unlike the ascending sensory pathway, the afferent pathway, this is an efferent descending pathway. So it's the primary efferent motor pathway. It involves conscious voluntary movement. And again, it is not a reflex. So we're starting in the brain this time because it's efferent. So an action potential, let's not get into how it's generated up there with the premotor center and all the rest of it, but the action potential starts within the pyramidal neurons of the primary motor cortex. Remember, this is the slice alongside the sensory cortex. And again, it's divided up into different areas, depending on where that action potential is going to go. It descends via neurons within something called the internal capsule. This is like a big tract, but it's arranged a bit like a filing cabinet. So the internal capsule, as you can see there, keeps the origin of those neurons all nice and tidy. So if they come from the leg, they go down the internal capsule in a specific part of the internal capsule. Yes? So they carry on down the internal capsule, and then they get to the medulla oblongata in the brainstem. In the medulla, these motor neurons enter tracts. These tracts are called pyramids. Don't ask me why. Now, in the medulla, most of the axons in these pyramids will cross over to the other side, to the contralateral side. And this is called the decussation of the pyramids. Decussation just means crossing over. We could say that in our pain pathway, that second order afferent decussed to the contralateral side. Just means crossing over. So this is a crossing over of these tracts called pyramids within the medulla. Some of them don't cross, about 10 to 20% don't cross. Instead, they go straight down and they enter the anterior corticospinal tract. The ones that do decuss go to the lateral corticospinal tract. If you want to remember it, that it's crossing over, you could say the contralateral lateral corticospinal tract. Now, the ones that don't cross mainly innervate the trunk muscles and the forehead. And this is often why people with strokes, their trunk and their forehead are not affected, because it tends to affect the decussed neurons that serve the limbs. So once crossed to the contralateral side, these are the ones that do cross, they descend via the lateral corticospinal tract. This is another tract going down the white matter of the spinal cord. At the relevant spinal level, they'll synapse with lower motor neurons, because what we've been talking about so far is the upper motor neuron. This is where the phrase upper motor neuron, lower motor neuron, lesions or disease comes from. So at the spinal level, the upper motor neuron synapses with the lower motor neuron. The lower motor neuron leaves the ventral horn, and of course we know where it goes off to a neuromuscular junction. And this is where we came in with excitation, contraction, coupling. If you remember, we said a motor neuron comes down to a neuromuscular junction. This is our motor neuron. It is the lower motor neuron. Upper motor neurons, however, may synapse with inhibitory interneurons rather than directly with the lower motor neurons. Why would we need inhibitory interneurons? Think back to our reflexes. We had to have inhibitory interneurons there so that we could relax antagonistic muscles. And the same thing applies with voluntary movement. So we want to make sure that the antagonistic muscles aren't going to contract at the same time so that our contraction is effective. Okay, so let's have just a quick look at the autonomic nervous system. If you remember, this has efferent and afferent branches. It can also be divided into the sympathetic and the parasympathetic nervous system. The parasympathetic nervous system, the purple colour there on the left, is all about down regulation. It's all about rest and digest. So it drives heart rate down. It slows everything up. The sympathetic pathway, the one on the right there in the green, is about fight or flight. So this is the thing that up-regulates everything. So this increases heart rate, it increases cardiac output, increases respiration, increases glycogenolysis, the breakdown of glycogen. All of this is designed then to up-regulate everything. And it works a bit like a seesaw. You don't switch one off and switch the other one on. What you have is a situation, and we'll come across how this is regulated intracellularly when we look at cardiovascular. You have like a seesaw of effects. So there will be a slight increase in the parasympathetic and a decrease in the sympathetic. That will make everything slow down. There will be a slight increase in the sympathetic and a decrease in the parasympathetic, which will make everything speed up. So it's a constant regulatory system, monitoring what's happening in the organs, in the tissues, and then regulating what's happening, efferent and afferent. So the parasympathetic and the sympathetic branches of the autonomic nervous system have opposing actions. But they can also be afferent or efferent. Afferent is monitoring, efferent is regulating. The sympathetic neurotransmitter, at least post-ganglion, the sympathetic nervous system has a chain of ganglia alongside the spine. Before then, they use acetylcholine, but after the ganglia, the neurotransmitter that they exocytose that binds to various receptors throughout the body is noradrenaline, one of our catecholamines, but in this case it's acting as a neurotransmitter. And this is partly why, of course, our adrenal medulla tends to release more adrenaline than noradrenaline, because most of our noradrenaline comes from sympathetic neurons. They can both bind more or less, most times, to the same receptors. The parasympathetic neurotransmitter throughout, preganglionic, postganglionic, wherever, is our old friend acetylcholine. Okay, so let's do some action potential revision. In your handout, I've left this blank, and you can then use that to either explain it to yourself or explain it to someone else, scribble all over it. Here, of course, we have the advantage of animation. So where do we start with this? We start at RMP, of course. Everything's closed, everything's fine, we're at resting membrane potential. Then we get some sodium diffusing through the cytosol from further along. That takes our little sodium channel there, the first one in the line, up to threshold. So from RMP up to threshold at about -50, -55, something like that. When that happens, when the voltage sensor hits threshold, of course that sodium channel will open, sodium influxes, and at that point in the membrane, we will have full depolarization up to about plus 40. So what happens next? Yes, that channel is going to close and gate, isn't it? So our sodium channel closes and gates. At the same time, our potassium channel now opens. We get a potassium efflux. That potassium efflux repolarizes back to RMP. Meanwhile, of course, the sodium that came in through that channel has also diffused out, and it's gone to the next channel along the membrane, the next sodium channel, and opened that one. So we've now got an influx of sodium further along the membrane. And that's going to carry on, of course, opening sequentially our sodium channels along the membrane. And of course, the reason it goes in that direction is partly because of that little gate on top of our sodium channel there when it closes, but also because of hyperpolarization. So remember, the potassium channels are slower to close. They delay closing until we've gone below resting membrane potential. We've gone into hyperpolarization. This, of course, is another thing that stops our action potential from propagating backwards. So at this point, we've got absolute refractory period because our sodium channel is gated, and we've got hyperpolarization. Of course, now we have to turn the tap off. So our potassium channel closes, and our pumps, now the channels are closed, can finally, our sodium potassium ATPase pumps can finally restore RMP because we've closed the channels around it. It will, of course, have been pumping the whole time, but it didn't stand a chance while the channels were open. Now it does because we've closed the channels. But of course, meanwhile, further along the membrane, our sodium channel, our second sodium channel is closed and gated, and our second potassium channel is opened, and we've got potassium efflux. So that right-hand part of the membrane is going back through what we just did before. And so it moves on progressively, propagating along the membrane. So this is action potential propagation along the membrane of the axon, all the way down to the axon terminal. Okay, so that's a straightforward, really, conduction in a non-myelinated neuron. But of course, nerves can contain both types of neuron, both myelinated and unmyelinated, and the conduction speed and the manner of conduction varies between them. So unmyelinated neurons, because we have to sequentially open channels all the way along the membrane, one after the other, it's quite slow. It's a slow conduction of action potentials. And certainly in sensory neurons, this can produce a dull, aching pain because of it. Myelinated neurons produce sharp, localized pain because the conduction speeds of that action potential are much, much faster because we have this conduction called saltatory conduction. And here we've got a myelinated axon. And you can see, of course, we've got our Schwann cells that have secreted myelin. Between the myelin sheaths, we've got these little gaps called nodes of Ranvier. Now, within those, we have a high concentration of voltage-gated sodium channels. We're going to have potassium channels and pumps as well. But all of the action is concentrated in that little node of Ranvier between the sheaths of myelin. So what happens is the action potential, the myelin is insulating, so the action potential skips from node of Ranvier to node of Ranvier. And this is much quicker than having to sequentially open and close channels all the way along the membrane. Instead, it's skip, 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 skip. Much quicker, much faster conducting. And this is called saltatory conduction. Large myelinated neurons, just to compare the two, can conduct action potentials at a rate of 40 to 70 meters per second. And you imagine how long you are and how long those neurons are going to be in comparison to 40 to 70 meters. We're talking a nanosecond for conduction to happen. Compared to unmyelinated fibers that conduct at a rate of approximately 1 meter per second. I know it doesn't sound a whole lot of time, but in comparison, it's a massive amount of time. So if you're over a meter and one neuron's got to go all the way from your toe up to your somatosensory cortex, it's going to take quite a long time to get there, comparatively speaking. Which brings us to synapses. Now, the thing about synapses is we've already talked about neuromuscular junctions. So what I want you to do is put that right to the back of your head. Don't forget it completely, but put it right to the back of your head for now. Because here we're talking about something that looks the same, but in a lot of respects is very different. For a start off, we've got a neuron synapsing with another neuron, not a myocyte. And that makes quite a difference. So at the synapse, we need to transmit our action potential chemically. So it came down the axon electrically, didn't it? So it now needs to be transmitted chemically, and that's done by neurotransmitters. Neurotransmitters are exocytosed from the presynaptic neuron, in other words, before the synaptic gap, and they then diffuse across the synaptic gap, and they bind to postsynaptic chemically gated ion channels on the postsynaptic membrane. Now, depending on the channels that are opened by that neurotransmitter, which depends partly on the neurotransmitter, this can create either an excitatory postsynaptic potential, or it can create an inhibitory postsynaptic potential, an EPSP or an IPSP. Both of these are graded potentials. I can't emphasize enough, these are not action potentials. These are areas of either local depolarization or local hyperpolarization. They are known as graded potentials, and they can be excitatory or inhibitory. So these are both graded potentials, which are local areas of depolarization or hyperpolarization. Depolarization, of course, being excitatory, hyperpolarization being inhibitory. So what makes this excitatory or inhibitory? Well, it depends on the channel associated with the postsynaptic receptor. So we're talking about the postsynaptic membrane here. Receptor associated next to a channel. Depending on that channel, and depending upon the particular neurotransmitter binding to the postsynaptic receptor associated with it, will depend on whether it's excitatory or inhibitory. Now, most neurotransmitters in their own right are not inhibitory or excitatory. Most neurotransmitters have inhibitory and excitatory receptors at different places. Often they have little numbers to identify them as different types of receptors. Now, excitatory postsynaptic potentials are going to sound very familiar because it's more or less what happened in our neuromuscular junction. But, as I said, stick that to the back of your head because we're then, of course, got to talk about inhibitory as well. So, excitatory postsynaptic potentials, the receptor that the neurotransmitter binds to opens sodium channels. And as we know, sodium always influxes. Sodium influxes, it gives us a local area of depolarization. So this is an excitatory postsynaptic potential or an excitatory graded potential. Inhibitory postsynaptic potentials, the neurotransmitter binds to a receptor that's either associated with chlorine channels or with potassium channels. Now think about our ultimate goal with inhibitory. We're trying to create an area of hyperpolarization. In other words, it's going to be more negative inside the membrane. So we can probably work out which way each of these is going to go. Yes, an influx of chlorine with its negative charge will cause hyperpolarization, or an efflux of potassium with its positive charge will also cause hyperpolarization. Remember, this is just local hyperpolarization. To explain it, we usually use our old friend acetylcholine, ACH, as our excitatory neurotransmitter and GABA as our inhibitory. GABA actually is inhibitory within the central nervous system, so it's not a great comparison, but these are the ones we're going to use. And you already know ACH. So, EPSPs and IPSPs are both graded potentials. They are both local areas of either depolarization, in the case of an EPSP, or hyperpolarization in the case of an IPSP. Let's have a look at one in action. So if we have an excitatory postsynaptic potential, we have our old mechanism that we know from basically neuromuscular junctions. An action potential travels down the presynaptic neuron, gets to the axon terminal. At the axon terminal, it opens voltage-gated calcium channels. Calcium influxes, binds to the cytoskeleton, and causes exocytosis. This is exocytosis of ACH. ACH is exocytosed into the synaptic cleft, diffuses across the synaptic cleft, and binds to chemically gated sodium channels in the postsynaptic membrane. Chemically gated sodium channels open, sodium influxes, and we get a local area of depolarization, a graded potential known as an excitatory postsynaptic potential. So an IPSP. So the change here is that we've got GABA. Same process to exocytose it. It's stimulated to exocytose by that action potential coming down the presynaptic neuron, opening voltage-gated calcium channels. Calcium is going to bind to the cytoskeleton and cause exocytosis, in this case of GABA. So GABA is exocytosed into the synaptic cleft and diffuses across, binds to chemically gated potassium channels or chemically gated chlorine channels in the postsynaptic membrane. If either of these channels open, then potassium effluxes, chlorine influxes, either of those is going to give us an area of hyperpolarization, an IPSP. Just a quick word on neurotransmitters. Neurotransmitters are inactivated in different ways depending on the neurotransmitter. Serotonin, GABA, and noradrenaline are inactivated by uptake, and we know about serotonin reuptake because we know about serotonin reuptake inhibitors. Dopamine diffuses away from the cleft and is actually excreted. We don't recycle dopamine. ACH is degraded in the synaptic cleft by acetylcholinesterase. This is an enzyme, obviously, that breaks acetylcholine into two. The choline part is reused, so it's taken back up in the same way as our neurotransmitters, their serotonin, GABA and noradrenaline are, but only the choline part of ACH is taken up. The acetate part is metabolized by the liver and then excreted. So different neurotransmitters are inactivated in different ways. So a single neuron, this is a postsynaptic neuron, may receive inputs from many different presynaptic neurons. So we've got the soma of the postsynaptic neuron, and we've got all these other neurons inputting to it. What they produce, these presynaptic neurons, are graded potentials. Graded potentials, of course, may be excitatory, EPSPs, or inhibitory, IPSPs. And these can happen at the same time in the same postsynaptic neuron, because we've got all these presynaptic neurons all inputting. If they're receiving action potentials, then they are going to create either an EPSP or an IPSP. In the soma, we never ever have an action potential. These are all local graded potentials. To decide whether there is going to be an action potential generated, the inputs have to be summated. This just means they need to be summed up. And this happens at a place called the axon hillock. The axon hillock is between the soma and the axon. In sensory neurons, it has a different position and it tends to be called a trigger zone. Now, the axon hillock contains a lot of voltage-gated sodium channels. These all have little voltage sensors, so they're able to determine what's happening in the soma in terms of depolarization versus hyperpolarization. The voltage-gated sodium channels at the axon hillock, they have a threshold of about minus 50 millivolts. So what happens is, to reach that threshold, we need a predominance of EPSPs. So we need a predominance of depolarization in the soma, as opposed to IPSPs, hyperpolarization. If we have a predominance of depolarization, then that threshold at the axon hillock may be reached. If threshold is reached, the sodium channels of the axon hillock open. When they open, sodium floods into the start of the axon from the soma. And of course, all along the membrane of the axon, we have voltage-gated channels. We have voltage-gated sodium channels, potassium channels, and sodium-potassium pumps. So that sodium flooding into the axon is going to open voltage-gated channels and set off an action potential that's then going to propagate along the axon. So this opening of these sodium channels, these voltage-gated sodium channels at the start of the axon, in the axon hillock, generates the action potential. This action potential is then propagated along the axon by the opening of voltage-gated sodium channels that are adjacent to the axon hillock. And then, of course, it will open the next sodium channel, and so on and so forth. And we have an action potential marching off along the axon in one direction towards an axon terminal. At this point, when it opens, the axon hillock has summated the graded potentials and it's generated an action potential. And that is the job of the axon hillock. It's to summate the graded potentials, whether they be EPSPs or IPSPs. And then if the EPSPs are more than the IPSPs, it will reach threshold and generate an action potential. So let's talk a bit more about summation, because there's various things that influence summation. Spatial summation is all about multiple inputs, all the different presynaptic neurons that are firing and are creating either EPSPs or IPSPs within the soma. It's also a little bit about the closeness, the proximity to the axon hillock, because imagine you fire an EPSP into the end of a dendrite. All along the membrane, you've got the sodium-potassium ATPase pumps. So by the time that sodium that influxed for an EPSP, or the chlorine that influxed for an IPSP, by the time it gets down towards the axon hillock, it's going to have diffused out, the sodium's going to have been moved out, so everything's going to be a bit weaker. So the closer the presynaptic neuron is to the axon hillock when it synapses, the stronger the effect will be. So spatial summation is about the number of multiple inputs all firing at the same time, or the proximity to the axon hillock, I should say, and the proximity really. So multiple graded potentials, EPSPs and IPSPs, are received by the soma. If there are more synapses creating EPSPs than IPSPs, threshold may be reached at the voltage-gated sodium channels in the axon hillock. And the closer the synapses are to the axon hillock, the greater the effect of the depolarization or hyperpolarization will be. Temporal, as the name might suggest, is all about frequency. So temporal summation is about the frequency with which each individual synapse fires. You imagine one presynaptic neuron has an action potential, comes down it, releases its neurotransmitter and creates either an EPSP or an IPSP. If it receives another action potential very quickly, it will reinforce that by creating another EPSP or IPSP, depending on its neurotransmitter. So temporal is about frequency, spatial is about multiple inputs. So if an individual synapse is receiving frequent presynaptic action potentials, it will create repeated graded potentials at the same synapse. And these could either be EPSP or IPSP. And this will increase the effect of that EPSP or IPSP because they're coming in too fast for the sodium potassium ATPase pumps to restore RMP. So they get stronger and stronger and stronger. In terms of summation, what that actually means is that a rapidly firing synapse creating one type of graded potential, EPSP or IPSP, may counteract multiple slowly firing synapses of the opposite type. So if we've got a soma that's receiving lots and lots of EPSPs from lots and lots of different presynaptic neurons, but we've got a presynaptic neuron that's producing IPSPs in the postsynaptic soma, and it's firing repeatedly, then it could counteract all of those because it's much faster. It's going poof, 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 compared to the other synapses that are just going poof, poof. So temporal summation can outweigh spatial summation and vice versa. So think about it. This is quite a good analogy as a bucket. This bucket has a small hole in the bottom that allows ions to gradually seep away. This small hole represents the sodium-potassium ATPase pump that's trying to restore RMP. Every time an EPSP is created, you tip in a mug full of pluses, a mug full of sodium. Every time an IPSP is created, you add a mug full of minuses, say for example chlorine. Each minus counteracts a plus, and each plus counteracts a minus. Both of them at the same time are seeping out of the hole. So if you put more mugs of pluses than minuses in, and if you do it quickly enough, so that's spatial summation and temporal summation, you will have more pluses than minuses. But if you are putting more mugs of minuses in, or putting them in quicker, the minuses will counteract the pluses in your bucket. So, if the pluses reach a certain number, in other words, the threshold of the voltage-gated sodium channels in the axon hillock, i.e. minus 50 millivolts, you don't win a prize. The voltage-gated sodium channels in the axon hillock open, and an action potential is generated. So you need more pluses in your bucket, and you need to put them in quite quickly. So let's have a look at that on one of Nikki's infamous diagrams. So here we have a postsynaptic soma. There's the axon hillock. There's our axon with its voltage-gated channels. Oh, and here we have an EPSP. We have an EPSP that is creating an area of depolarization. That's going to diffuse towards the axon hillock. Not enough yet to reach threshold. And then we counteract that with an IPSP, creating an area of hyperpolarization that is counteracting that EPSP. Oh, but now we have another EPSP. So we've got more pluses coming in, more depolarization, and guess what? It's a bit closer to the axon hillock. So it's going to have a bit more effect. It's going to remain stronger longer. But then we have another IPSP. It's nearly as close, and it's counteracted we've now got two EPSPs, two IPSPs, and they're all counteracting each other. At the moment, it looks unlikely that we are going to reach threshold at the axon hillock, and those voltage-gated sodium channels are going to open and flood sodium into the axon. Until. But before, we have our little IPSP there down there, fired again. So that's temporal summation. What it's done is it's strengthened its IPSP that it's just created by creating another IPSP on top of it. So it's looking even less likely that we're going to reach threshold at the axon hillock. But then finally, we have another EPSP, fairly close to the axon hillock, so it's nice and strong. And look, it's counteracted the IPSPs. Our axon hillock, the little sodium channels in the axon hillock, voltage gated, have reached threshold, they've opened, and we've got a flood of sodium going through into the start of the axon. This is then going to propagate an action potential along the plasma membrane. So that was neurophysiology. That was actually our fourth topic, so we're sort of more than halfway through. Our next topic is immunology, but before you move on to immunology, then please make sure you've got neurophysiology more or less lodged in your brain. And certainly by now you should be having a study buddy and you should be trying to explain this to people. And don't forget to go back to early material and go over that again. It often helps to revise something several weeks later to help strengthen those memory pathways.